minus 2 on both the top and the bottom. This is going to tell us our whole. Let's cancel those out, and let's say that our whole is where x minus 2 is equal to 0. If we move the 2 over, we'll have x equals 2 for our whole. Now, it's not going to be enough to get just x. We need to get y to go with x. We can say that y is going to be whatever's left over. X squared plus 5 over x plus 5. And we're going to let x equal 2. So we'll have 2 squared plus 5 over 2 plus 5. If we do the math, 2 squared is 4. Add 5 gives 9. And 2 plus 5 on the bottom gives 7. So we can say the whole exists at 2, 9/7. You must give an x and give a y. Giving one or the other won't be enough. But here's our whole right there. Now for the vertical asymptote. We're going to set the bottom equal to 0 and be sure to ignore the whole that we just found at 2 9/7. So we'll say x plus 5 is equal to 0, move the 5 over, and we'll have x equals -5. For the vertical asymptote, you don't need an ordered pair. You need a letter, and you need a number. So that takes care of the whole and the vertical asymptote. Now to find the horizontal asymptote or diagonal asymptote, we have to use different rules. Notice I've already canceled out the whole, and now we have an even further simplified version of our expression, x squared plus 5 over x plus 5. To figure out what to do here, we have to check our powers. So I'll call the power on the top n and the power on the bottom d. The power on the top is second power, and the power on the bottom is just x, that's first power. So if n is greater than d, that means if the power on the top is greater than the power on the bottom, you have no horizontal asymptote. The answer to that is automatically d and e. However, you do have a possible diagonal. To find that diagonal asymptote, you would have to use longed division. We'll do that in a moment, but before we go on, I want to go over the other possibilities. If the power in the numerator was less than the power in the denominator, we have an automatic answer of y equals 0 for our horizontal. And if you have y equals 0 for your horizontal, you have no diagonal asymptote. If the power on the numerator and denominator is the same, you'll need to divide the leading coefficients. And you say y equals whatever number you get when you do the division. Again, you would have no diagonal. However, looking at our powers, we can see that the numerator's power is definitely higher, which means we have no horizontal asymptote, but a possible diagonal, and we'll have to use long division to get it. So let's try long division. We'll have x plus 5 in the denominator, place that on the outside, and x squared plus 0x plus 5 on the numerator, we'll put that on the inside. Notice how we have no x term here in the numerator, so I placed a 0x as a placeholder. Now let's do the long division by taking the leading terms, starting from the inside, going to the outside, x squared, divide by x. Well, if we divide, we get x. Place that in the first position, and multiply that times the x and the 5. X times x gives x squared. X times 5 gives 5x, and we change both signs. So the x squared drops out, and 0 minus 5 gives negative 5x plus 5. Now, divide the leading terms once again. Negative 5x over x gives us negative 5. Now, we take negative 5 times both of these, negative 5x. Negative 5 times positive 5 gives negative 25. Change both signs so that the 5x drops out and you get 30 as your remainder. However, your diagonal asymptote is just going to be the quotient. So you can say that your horizontal asymptote does not exist, and your diagonal asymptote is going to be y equals the x minus 5 we got for our quotient. Now we can move on to problem 8e and 8g, again using the simplified rational function that we had previously. Find the x-intercept and y-intercept of the function. For the x-intercept, we're going to set the top part of the fraction equal to 0. So we'll have x squared plus 5 equals 0. Subtract 5 from both sides will give you x squared equals negative 5. We would ordinarily solve this by taking the square root at this time. This would give us x equals root of negative 5. However, this number is imaginary because it is a negative inside of the square root. Which means for this question, if you ever get an imaginary answer for an intercept, you can automatically say DNE, it doesn't exist, and it won't appear on the graph. Now for the y-intercept. For this, we're going to set x equal to 0. So we can say y equals 0 squared plus 5 over 0 plus 5, which gives us 1. So we can say our y-intercept is 0, 1. Remember, you must give an x and give a y. It's not enough just to say 1. So we have no x-intercept, doesn't exist, and our y-intercept is 0, 1. Now let's try to actually draw the graph. I've collected all the information we found previously. We have a vertical asymptote at x equals negative 5, no horizontal asymptote, a diagonal asymptote at y equals x minus 5, a hole at 2, 9/7, a y-intercept at 0, 1, and no x-intercept at all. Now let's try to draw the graph. First, we'll place the vertical asymptote at negative 5. Put a dotted line there. You will not be able to cross that line. We have a hole at 2, 9/7. Should be over here somewhere. We have a y-intercept at 0, 1. Should be over here somewhere. We have no horizontal asymptote. We have no x-intercept, so we'll never cross this line right here, this x-axis, and we'll have a diagonal asymptote at y equals x minus 5. That's going to be down here somewhere. This is going to be a diagonal line starting here, and it's going to go this way and this way. It's not a perfect diagonal line, but it's close enough for our purposes. Now we can see that we have this triangular region. What we're going to do is we're going to draw a line next to this vertical asymptote. We're going to let it curve, cross through the 2 points we've just made, and then let it run along this diagonal line over here on the right. To get the rest of the curve, we'll need to hop through this angle that the asymptotes have created and again draw a line that runs along those asymptotes. Doesn't fit particularly well on this graph, but you get the idea. It's not a perfect graph, but it's good enough for Mat-171. Thank all of you for watching, and we'll see you again soon.